Thank you again for the opportunity to speak. Okay, so what is this? Let me start to introduce it like the slogan, at least the idea. So if after lunch somebody asks you what was the talk was about, and you're like, okay, well, enumerative geometry is counting problems, right? But then this A1 is counting problem now for arbitrary fields. So usually you do things over the complex because you get invariants, right? But then this A1 is now arbitrary fields. So let's say the rationales, the periodics, it's kind of like an universal theory of that. And then these tropical methods, it's this combinatorial methods from tropical geometry that apply for toric surfaces. So I won't go into the details of tropical things, but we can just say, this is enumerative geometry for toric varieties or arbitrary field. And well, I say arbitrary field because, sounds good, but we will talk about perfect fields of characteristic not 2. So for characteristic 2, there are options to say things. It's just the presentation is very different. So we will adjust for the sake of a better presentation. We won't take it into account. And the perfectness, we use it a lot. So that is something, sometimes we can skip, but most of the time we will need it. So that is for me an arbitrary field. And of course, all the problems that we talk about is just generic configuration, generic points, so the generic case, right? So what's the plan? So I will give the definition of the Grothendieck ring for those that don't know. So it's a very classical object, but it's not very known because I guess there's not a lot of application outside of this, but there is a very natural thing that comes in this A1 enumerative geometry. Then I will give an example that is lines of surfaces on cubic, well, explicitly lines of cubic surfaces. That is something very classical. We prove a theorem in intersection theory over for toric varieties. And then lastly, I will talk about arithmetic from fit and invariance. So this is Kerr counting. So all of these are, let's say, classical problems in enumerative geometry. If you don't know, then that's okay. I will introduce them. And then so let's start with the Grothendieck ring. This is our main player, right? So this is the space where we're going to count. So this will replace the natural number, or well, for the complex, or it will replace the integers with the reals, because this is like the classical fields where we are used to count. So what is this Grothendieck ring? So it is the ring of isometric classes of non-singular quadratic spaces. So that is just quadratic forms up to isometry. Of course, we take non-degenerate. And then we have some, we have a presentation that is very nice. So it is generated in degree 1 by these forms that we call bracket A. These ones, right? That just goes from K to K, right? You take X and then you send it to X squared. We have non-degenerate forms, so A cannot be 0, so we take units, and that is all the generators that we have. And then we have the following relations. So, of course, if we talk about isometry, right? If we have AB squared, X squared, this is the same as A BX squared, right? So the form generated by A is the same as this form generated by A B squared, which means that from all the generators, we actually only need to consider the units, right, up to the units squared. Yeah. And then we have a tensor product. This is a ring. It comes with a tensor product, which tells me that the form generated by A times the form generated by B is the same as the form generated by AB. And these two relations on the sum, that is, it comes from classical linear algebra. So actually, if you sit down, you can see that you can find a matrix always that sends this the form generated by A plus B to the form generated by A plus B on one side, and then A plus B times IB on the other side. And of course, this is when A plus b is an unit. But if a plus b is 0, we have a different relation. And then this relation, it uses that the characteristic of the field is not 2. So a plus minus a is 1 plus minus 1, whenever the characteristic is not 2. And then this form, we were going to call it h, the hyperbolic form, and then that it will come out a lot. So that's why I put it in red. So examples of this field, okay. So if your field is algebraically closed, right? There's only one generator because everything is a square. So for the complex, there's one generator, all the relations, then they are trivial. And in that case, well, we have a free group in one generator that is just said. And then this isomorphism is given by the rank, okay? So the rank takes a correct form and then it just sends it to the rank. Now over the reals, we have the Sylvester theorem that tells us that a non-degenerate real form, right? It is determined by the rank and the signature. Now we have for R, sorry, this should be bold R. Now we get, this is generated by 1 and minus 1. Yeah, this is just 2 copies of that. But the important part for the reals is that the rank and the signature, it determines your correct form up to isometry. Okay, so what is the width group? So the width group is the quotient of the Grothendieck ring of the, or group of the field divided by the ideal generated by H. So this is just, well, it's a different group, but when we do arithmetics in the Grothendieck ring, it's just easier sometimes to just send the ideal given to H to 0, because an element in the Grothendieck ring, so a correct form, it is determined by the rank and the class here, right? Because then if we know the class in WK, then your form is just this class plus a multiple of H, an integer multiple of H, in such a way that the rank is fits. Okay, so another tool from these big groups of correct forms is the trace form. So if I have a separable field extension, right? Let's say K in L, then there is the trace form actually induces a morphism at the level of groups. So we'll have that the trace from L to K and actually goes from the Grothendieck ring of L to the Grothendieck ring of K. So whenever I take a quadratic space, a quadratic form from a vector space B to L, then I can send it to the composition, right? From my quadratic form composed with the trace. So the algebraic trace, right? This is the trace of field in which an element is sent to the sum of all the Galois conjugates, right? So what we're doing here is we take alpha, which is a correct form, from a vector space, L vector space to L, and then we compose with the trace from L to K. So the composition, if you see, is, right, this composition is a map from a vector space to K, and then all we need to, let's say, change V from a L vector space to a K vector space, right? But it is the case because for a separable field extension, right, L is a vector space over K. So as an example, well, the trace of the complex or the reals, so this morphism is just going to be determined from the image of 1, right? Because we saw that for C, this is just set, is generated by 1. And then, well, this is, let's say, this is an exercise for linear algebra, that the trace of 1 is going to be 2 plus minus 2. Yeah? But then from the relation that we saw before, 2 plus minus 2 in R, this is the same as 1 plus minus 1. And then, well, this is just H. Okay. And then let's say this is the reason why H will appear a lot. Okay, so let's do our first example. This is, let's say, the motivation. And one of the first examples that had like started all this theory of enumerated count. So here I will give this motivation example and sort examples about toric surfaces, but there is a lot more things that have been done in the literature following this computation from A1 enumerative geometry. So when we talk about lines on a cubic surface, well, projective cubic surface that is smooth, the generic case, right? So over the complex, this is a very classical statement that there are 27 lines. Yeah, okay, here I put even for singular surfaces, but let me talk about now only smooth. And that is an invariant. Actually, we can compute it as a degree of a Chern class of the tautological bundle over the Grassmannian of lines. But that is, let's say, the proof. But it is a very classical statement. There are 27 lines, and there are actually many other proofs that this is the case. Now, over the reals, well, it depends. Right? As always with the reals, it depends what your polynomials are, what your equations are. So it's going to depend on your surface, right? It can happen that there are 27 lines, and this 3D printing, right, of objects that we see in many math departments, but there could be also 15, 7, or 3, depending on the surface setup. So what happens over the reals is that these 27 lines, we can actually divide it in 2 types. We can say that they are either hyperbolic or elliptic, depending on the determinant of the bilinear for associated domain. So we're going to details for this, but let's just believe that all these numbers have this division. So when you have 27 lines, you get 15 hyperbolic lines and 12 elliptic. Or you get 15, you get 9 and 6, 5 and 2, or 3 and 0. And then there is a theorem from Segre from the 40s, so 80 years ago. So it's classical, but not that classical, I guess, that tell us that the difference is always 3. And then, well, there is a generalization of this statement. There's a theorem from Castle Bickelgreen that if we have now a smooth projected cubic surface, then the number of lines contains on it. So the sum of the type, right? This is going to be 15 times 1 plus 12 times minus 1. And then this is an invariant that lives in the Grothendieck group of K of the field. And well, if you see here, right? So the rank, this is a prime form of rank 27, right? And the signature is string. So that okay, that remark I put here, right? Which tell me this computation actually records what is happening for the complex case and the real case, but this is an invariant that works for arbitrary field. So actually it's something that records what happened for algebraically closed fields and for real fields. So not only the real, but if I have a field that is a number field or a real field, it will have all the arithmetic information of it. So what happened here, let's say in the case of the real, so if I have the 27 lines, right, then the type being hyperbolic or elliptic, it will coincide with having a 1 or a minus 1. But if I have less real lines, so let's say I have 15 real lines, I'm going to have 9 lines that add to 1, 6 lines that add to minus 1, and I'm going to have 12 lines that are complex conjugated, right? So these 12 lines, there are 6 pairs of complex conjugated points. So it's 6 times h that are appear here, and that is what makes, let's say, the discrepancy. Okay, This was, let's say, the motivation. So now let's talk about intersection theory. Well, at a very elementary level, let's say, just intersection of hypersurfaces in Pn. So this is very classical. This is the Bézout theorem. And there we talk about complex projective space, right? So we have intersections. Just give me a second. Sorry about that. Okay, so the Bézout theorem is already complex, very classical theorem. So now we have two directions for it to generalize. So there is proof of the Bézout theorem for arbitrary fields. This has been done for McKean in also 2021. And over the complex, there is a generalization of intersections of hypersurfaces, not on Pn, but in a toric surface. So you have now a toric surface, and I have hypersurface, and then there is the Bézout theorem, but for Bernstein and Kuznichenko theorem that tells me that the product of these in hypersurfaces is given by the mixed volume of the degree. And what we proved now is, let's say, an enriched now Bézout theorem. So this will specialize when we take, this is for toric surfaces, toric varieties over arbitrary fields. So when K is equal to C, we get this direction, right? And when the toric surface, right? So with delta is our delta standard, that means that the toric surface is the projected variety, sorry, the toric variety is the projective space. Then in that case, we get this Bézout theorem. And all of these are generalization of the Bézout theorem for the complex. So this is just to show the directions. Let me state the theorem. So this was proved by McKean in 21. Now, what does it say? So now it says if we have now n hypersurfaces of degree ti, that means that this is a section of this vector bundle, right? So that means we're taking the vector bundle given OPN of D1 plus OPN of D2, right? So the section of each of these bundles are polynomials, homogeneous polynomials of degree ti. That's why a section is just give me n homogeneous polynomials of degree ti. Then he has a condition about the orientability of this vector bundle. So let's say this vector bundle is relatively orientable if the sum of the degrees is congruent to n plus 1 mod 2. Then in this case, we have that this number, which is the Poincaré Hopf number of this vector bundle. So this is just the number of intersections counted by multiplicity, right? This is what we have here. This is the sum, right, over the zeros of this section. So this is the zeros of the polynomials that I have, right? And then, well, I have the sign of intersection, right? So the sign is just, in this case, the determinant of the Jacobian at a point P, right? So that means that over the complex, remember this, over the complex, this is just always 1 up to squared, but not over the reals, right, or arbitrary fields. Then here we have the determinant of the Jacobian, we put it in brackets, and then what McLean's claims is that if we sum this number, right, over the intersection of the hypersurfaces, what we get is the product of the degree divided by 2 times h, right? So this numerical condition of the degree, that the sum of the degrees is congruent to n plus 1 mod 2, that implies actually that at least one of the degrees have to be even. Then the product of the degrees is even, is divisible by 2, and then we get this equality, right? So if we now take the rank and the signature of these, right? we get this. The rank of this form, because H has rank 2, is the pair of the degree. So that is the classical Bézout theorem over C. And the signature is 0. And then why the signature is 0? Well, we can see that over the reals, basically, if you take two curves of degrees of different parities, right? What we're doing here is summing the sign of the determinant. But then here we just have frames. Basically, what we're doing here is we're saying that the sum of these frames, it goes to 0, right? So we're going to have plus, minus, plus, minus, plus, minus, and we have the same number. That's why the signature of this form is 0. Okay, then that is what we generalize. So on the other direction, so this is over C. Right. So now we have hypersurfaces in a smooth Tauri variety, and now, well, now the degree of the hypersurface for like a general Tauri variety, this corresponds to a Newton, a lattice polygon, and then this is just the Newton polygon of a defining polynomial, right? So the hypersurface is KVI. This is the zeros of a polynomial Fi. It just is not an homogeneous polynomial. Now it's a polynomial. It depends on where it lives. And then delta I here is the Newton polynomial of Fi, right? And in that case, well, the number of intersections, this is the mixed volume of the Newton polygon. So for, let's say for P2, as an example, then for P2 is the standard delta n that we get, right? Because we get, if I want to write down a polynomial, this is, I will have xd, right, plus terms, yd, plus mixed terms, plus a constant, right? Or in homogeneous coordinates, they will be z to the d, and all of these with constants. 0d, a d0, right? So this will give us a triangle of vertices 0, 0, d0, 0d. And then the mixed volume of 2, just to set an example for those that are unfamiliar with these, say delta 1, delta 2. This is the area of the sum, delta 1 plus delta 2, minus the area of delta 1 minus the area delta 2. Okay. And then, well, if we have two triangles like this, then the area of the sum is a triangle. So let me draw this. Okay. This is truly a mixed volume. So this is delta 1 plus delta 2 in this case, right? And then, well, the area of everything minus the area of each triangle, this is just d1 times d2. Okay, but in general, it's this mixed volume. In higher dimension, the definition is a little bit more complicated, but that is what it is for toric surface. So this is also a classical theorem from the 80s, late 80s. And then what we did is, well, in a joint work with Sabrina Pauli, we proved this now for arbitrary fields. So now if we have these tropical hypersurfaces, or let's say these are hypersurfaces in a toric variety, then what we have is now the intersection. So now the sum over the intersection product of the multiplicity or counted multiplicity. So now this is a mixed volume divided by 2 times h plus an error form. And then this error is, we can compute the rank, right? So these are all AI. The rank is bounded by this combinatorial statement. This is the number of odd points in the boundary of the Minkowski zone. Let's say for the case of P2, again, if we have the sum, right? This is a triangle of size D1 plus D2. Well, if we want to compute this, the number of odd points on the boundary, we get two cases. Either D1 plus D2 is actually odd, and in this case, there are no odd points, right? Why? Because, well, what are the odd points here? So the points on the boundary, well, here, they all have an entry 0. This is, sorry, 0 something. Here, there's something 0, right? And then on the boundary, I can write it as being D1 plus D2 minus LKM, M, right? So if D1 plus D2 is odd, then this cannot happen, right? So if you remember, this is the numerical condition that McKean had. So D1 plus D2, it needed to be 2 plus 1 or 2. So in this case, the error is 0. So that is, let's say, a small proof that this is a generalization of the Bézout theorem that McKean had. But now this is valid for arbitrary fields. And then the proof, we prove this using tropical geometry. But yeah, the proof is really technical. So I will just prefer to focus on the statement, because also the statement is already technical for people that are not familiar with geometry. But yeah, so this is statement. So if there's questions, it will be a good time. If not, then let's move on.
Can I maybe quickly ask, when you write enriched tropical hypersurfaces, what do you mean with this enriched?
Okay, so right. So actually, what we want to prove is for hypersurfaces of toric varieties. When we want to prove this, actually, this intersection, when, well, we use the tropicalization map. But the tropicalization map, it loses a lot of information. So usually basically you just keep the exponents on a very large scale of putting the things out. This enriched tropicalization now, it also records the coefficients of the leading terms, basically. Yeah, it's a little technical, but you need to know the sign of the coefficients. Well, for the reals, you need to know the sign, and then for arbitrary fields, you need to know the sign, meaning the class of the coefficient up to square.
Okay, so got it. Thank you.
Yes. Okay, this is what I was saying, that in the particular case, then this is. Okay, now let's move on to this Gromov-Witten invariance and Belgian invariance. So, well, Gromov-Witten invariants come from physics, and they are more general than this, but for P2 at least, the most classical one is just the number of curves that passes 2 points. So in D is the complex one. So now we fix a degree, and now we count the number of degree D rational curves. So all of this story is for genus 0. So in the complex, it works for arbitrary genus, but we in our case, it only works for rational curves. Right, and then, well, we need to fix points. So for rational curves, we need to fix 3D minus 1 points. And for the complex case, then, well, this is an invariant as long as the configuration of points that you pick is generic, right? So let me just put it here as an example. In 1, that we can all compute if d is equal to 1. We're talking about lines that pass through 2 points. And then this is very independent of the complex. Similarly, in 2, these are conics that passes through 5 points. And then, well, we can do this by using linear algebra and then putting all the coefficients, right? We get 6 coefficients and 5 points that give us let's say, a dimension 1 space, and then this is independent of the field. And because we actually, once we have a polynomial defining our conic, we actually don't care about multiples of it, then we actually have only one. Okay, that was very fast to prove that this number is 1 and independent of the complex. Okay, and for degree 3 is the first that is non-trivial. Now, if we count cubics, rational cubics that passes to 8 points, then this is the first one. Now we get 12. This is also a very classical computation. And then, well, in general, that is the case. Let me just put for completion, and for x is 20, and so on. Okay, so this is over the complex. They are invariant. The invariant comes for free. Now, WD, this is called the Belchamp invariance, and it's now the number of the rational curves now in RP2. So now we're counting only real curves that passes through a generic configuration of points. So as before, this is the naive count is not an invariant, right? So I can put W1, it's 1, real lines that passes through 2 points, and conics that pass into 5 points. Real conics. This is the only one. Now, for W3, we will have naively, so if we have a real points, and we count conics that passes through these points, we may have 10, well, we can actually have 12, 10, or 8, right? So that depends on the configuration of points. So it's not invariant, naively invariant, right? So the number of curves, that is not an invariant. It depends on the configuration. But over the reals, we can do a sign count, right? And then what happens, at least for the cubics, is that there will have curves that have these kind of nodes, right? Where x squared minus y squared is 0 locally. Or we can have these invariants, these kind of nodes, sorry, where x squared plus y squared is 0 locally. And then what happened here is that when we get 12 curves, we get 10 of one type and 2 of the other type. And then we get 10 curves, we get 9 and 1. And when we get 8 curves, we get only 8. So that tells us, right, that is the correct thing to look up. And then, well, W3 is going to be 8. And so on. So the number of these points is what we call the number of isolated singularities, real singularities. So WD, now if we count with the sign, this is an invariant. That is a theorem from Bézout from 2003. So this is, we're getting closer and closer in the timeline, I guess, right? And then, okay, those are invariant. Now, how do we compute them, right? So this is what I was saying before. So at least for the first non-trivial invariant, right, or the reals, that is not, the naive count is not invariant. And now, well, how do we generalize this sign now for arbitrary fields? And then, well, this is an idea of Mark-Levin, and that tell us, well, we're looking, right, at local branches. So generically, the only singularities of these curves are nodes. So to a single node, we should also say +1 or -1, depending, right? Of basically we get a square plus a y square. And then he says, well, we need to keep track of the a, right? How do we keep track of this a? Well, we take the Hessian, right, of this equation, which is just 2 and 2a, right? And then we just take the determinant. So the determinant of this Hessian, right? Well, this is up to squares, this is a. And then that is what we need. Well, technically, just to coincide with the real, right? Because the reals of this, we just use minus the determinant. Right, because just to make it coincide with the reals. This minus is just let's say a convention. But then that's it. We need the determinant of the Hessian. Now, what it may happen is that the node, it leads on a field extension, right? So I have real curves. Then it may happen that I have pairs of imaginary complex conjugated imaginary nodes, right? Of complex conjugated nodes. So in this case, we take the norm, right? So the norm of the field extension over the field of definition of the curves. This is something that lives on the curve, and we just take the product over the nodes. Yeah. So, I mean, all of this is just to say that if your curve is defined over the reals, then this is just -1 to the number of elliptic points. And it's it. So this is how we define now the contribution. So this is the realization of the sign of the curve, right? On this, I will put it on the field of definition of the curve. So now if you want to count curves on a field-based case, then we need the trace. That's why I introduced the trace at the beginning. So the trace reappeared here, right? So that is the multiplicity that we want, right? The multiplicity of the curves over the real, over your base field K. Then this is the trace from the field of definition of the curves to the base field of this product of nodes. Basically, all this bit bracket is just the product of over the nodes of this A element. So just tell me where the branches live, let's say in total. And then, well, this is the correct sign, let's say, in a sense, right? This is a theorem from Cass, Levine, Solomon, and Bickelgreen from last year that tell us that, well, if we actually count the number of rational curves in, not RP2, sorry, AP2, that passes through a configuration of 3 minus 1 points, and now K points. Well, they prove it for points, but what we prove is for K points, so let me just state it for K points. Counted with the sign, then we get an invariant. So this does not depend on the configuration of points. And they prove it by showing that this is the degree of a map. This is an A1 degree within this theory of A1 enumerative geometry. So this is the degree of the evaluation map from a multi-space that they construct to a configuration space in such a way that if your configuration now is generic, then the degree is it gives the number of curves with this sign. Okay. And then, well, what they have is that the rank of this A1 invariant of A1 Gromov-Witten invariant is the complex one, and then when your field is real or contained over the reals, right, then the signature of this coincides with the Belgian invariant. So as an example, they actually compute N3. So this is the number of cubics passing through 8 points, rational cubics passing through 8 points for arbitrary fields. And then they have that this is 2 times h plus the sum over the trace of the field of definitions of your points of 1. So here we will restrict to K points. So if they're all K points, then, well, the trace is trivial, right? That means a K point means that the field of definition is K, and then the trace from K to K is the identity. So in that case, we have 2h plus 1. Then we can remark that the rank is 12, right? Because h is a form of rank 2. And the signature is 8, because the signature of h is 0. Right, so this is, let's say, a first example, but they compute this N3 a little by hand. So the number of let's say, cubics, the classical thing, it's, I mean, you can also kind of compute it, but you can compute it, when I say by hand, is using that you have only one node, so you really need degree 3. And So it doesn't work in general. Let's say this method, it won't allow to compute anything more than entry. There are other examples for invariants that you can define for other surfaces. But the question now is, how do we compute this invariant? So they proved that it's invariant, right? And now the question is, how do we compute this? So let's go back to the history of this invariant for the complex case, right? This is, there's Conceivit's recursion formula that tells me that, well, ND actually can be computed in terms of the lower invariance. You just need that N1 is equal to 1. Now, for the Belgian invariance, actually, it's not true. Over the reals, there's no social recursion, easily recursion formula. There is a Caparazo-Harris formula, or by Caparazo-Harris, that actually it tells us that we can define relative invariance. So these are now our count curves with respect to a line. So we fix the degrees and the convergence points, but we actually fix the intersection with your curve with a baseline. And then we have a recursion formula for these two. So this is for the complex, both cases, let's say original cases, and now the Caparazo-Harris formula. That one can be modified in such a way that we can compute the Belgian invariance. So this will apply for WT. Fine. Okay. Well, and there's another element of this story is Minkowski's correspondence theorem that tells us that the complex and the real counts can be computed tropically. What that means is that we can actually count the number of the number of tropical curves with a fixed multiplicity that give us the complex and real count. Okay, and then what we prove together with Sabrina is that this A1 Motivic, okay, A1 Gromov invariant, right, it can also be computed through this correspondence theorem. So of course the correspondence theorem have to be adapted. But basically we now have a configuration of k points. We can pass through the Bézout series. So that is, let's say, a crucial element in the use of this tropical theory. And we can tropicalize, and then the tropicalization produces a multiplicity that is non-trivial. I mean, that is different from the complex and the real one. It lives in this Grothendieck group. And now if we count tropical curves with this multiplicity, then we get an invariant. Yeah, and then actually as a corollary of this, if all the points are k-rational, so okay. Well, this is P2 of R. Oh no, sorry, this is R2. My bad. Yeah, no, these are the real, the tropical curve. Yeah. We fix 3D minus 1 points in R2 through a generic configuration of those, and we count the tropical curves with this quadratic multiplicity. Then we get this equality, and actually as a corollary, if all the points are k points, then we get that this Motivic invariant, it is defined, it actually equals, well, this equation, but it is determined by the complex and the real realization. And well, there is, let's say, kind of like a philosophy for this, and is the fact that this problem, the enumerative problem, it can be defined over the integers. So the integers is not a field, but we can actually ask ourselves, well, what happens if all of the curves that we're considering, they are defined over the integers? And then say the heuristic of this A1 enumerative geometry is that if you can define your problem over the integers, then you're going to have your Motivic solution. It will be multiples of 1 and minus 1. So this setups for the case of k-rational points. And together with Hannah Marvik and Philip Furley, we actually have now a Capurraso-Harris formula. So this is, don't care that much about this very long and big formula. What is important here is that now we have a recursion formula that is algorithmic, so we can put it in a computer and we can actually compute this Motivic invariance by the use of recursion. So we just, all of this will just go back to the case that n1 is equal to 1, and we'll just compute this using the classical Capurraso-Harris adapted to our case. And well, you can ask about point conditions on field extension, right? So I said as before, right? All this talk was about now configuration of points that are purely k-rational, but of course this is not always the case, right? So for the reals, for example, you can also ask about real curves that passes through some real points or none, and some pairs of complex conjugated points, right? So as an example of that tree, so now let's say WDF, right? So now let's do, this is the number of rational curves. Now passing through a configuration of, let's say, T plus 2S. This is equal to 3D minus 1. So this is T real points and S pairs of complex conjugated points. This is pairs of points that are complex conjugated. Right. So in this case, we can also ask about this number of curves. It is also an invariant when we count this curve with the Belgian design. And then here I can say that W3 of S, this is just the 8 that we have, minus 2S. Right. So there is, I prove, let's say, a wall crossing formula. So now if I have 2 points, right, that are k-rational, and then I made them collide into a double point that is also k-rational, and then disappear to a pair of points that are conjugated, but now not complex conjugated, but you know, they live in a quadratic extension, right? Then we have a relation between the invariance on the left-hand side and the invariance on the right-hand side. And then, well, what is this relation? Is that if I consider now the curves that passes through points, well, a configuration of points where we have 2 k-rational points, and a configuration of points where we have the same other points and now a pair of conjugated points, then the difference of these two, right? So this is the one with k-rational points, right? And then this is the one with the pair of k-rational points. The difference of these two is a multiple of the blow-up. So now this is the intersection, because this is the other points. And now this is the curve that passes through the blow-up of X with the same degree, but now, well, this minus E, it means that it touches the sectional divisor in two points, right? So basically, we're really counting curve that passes through this middle point. So basically here, we just do the blow-up of X in this point, right? So this will allow actually to also compute invariance now for configuration of points that are not only k-rational, but also we have points that lead to extension. So let me just use this example here, right? So let me just go through this example a little bit in detail. So this actually, it comes from our theorem with Sabrina, our correspondence theory. This is going to be ND. So that was 620, sorry, M4. minus W4, which is 240. And then we divide it by 2 times H plus W4 times 1. Yeah, so this is the invariant for all k rational points. That's what k P0 means. And now, well, with this formula that we proved, right? So this gives also a recursion on a different thing now, right? This will tell us that the A1 invariant, say, of D in Pi plus 1, this is the A1 invariant in Pi plus delta, and then this is the invariant in D minus 2E of the blow-up. So let me put this for the blow-up. You know, Pi. So, okay, so right. So if I want to compute now M4 of like P1, so having one pair of conjugated points, this is the invariant from P0 plus a multiple of the invariant from the blow-up. And then, well, we can use this formula several times in such a way that we actually add one pair of conjugated point each time. So here, beta 1, this is where the field of definition of the conjugated point. So this is the trace over k square root of D1, let's say, over k of 1. And so on. So now N4 of P2, this is just now a polynomial in the Grothendieck ring of beta 1 and beta 2. Now beta 2 is the trace of the field of definition of maybe another field extension. Because now for arbitrary field, let's say over the rationals, right, I have infinitely many degree 2 extensions, which is something very different than from the reals, in which I have only one degree 2 extension. And then, well, doing this by induction for degree 4, we're talking about 11 points. So I can have up to 5 points. And these actually, it will also be, let's say, I don't want to say a universal polynomial yet, but it will also apply for k-rational points. So here, if actually the 2 points I was talking about, right, they are defined over k, then beta I, we can just replace it by a 2. So actually this last equation, it works for all configurations that are k-rational or a mix of k-rational points and points that are defined over degree 2 extension. So well, now, well, the question will be what happens for field extensions that are now arbitrary or like, well, degree 3, degree 4, degree 5. And well, this is still an open question, and this is what we are working about. So the work in program is, well, understanding these local multiplicities, and then a general correspondence theorem that will be, okay, general for arbitrary field extension or points that are defined there, and wall crossing formulas, so formulas as the last formula that I proved now for arbitrary, right? So that will be, now if I take a configuration of, let's say, p points that collide, so this is x, let's say, to the n minus t, that collides to a point of multiplicity m, and then, well, they actually disappear from the map, so they will go to a field extensions that will be a Galois orbit that exchange all of them, right? Then I can still have a version of counting curve that passes through this point, right, by the theorem of Cass-Levin, Solomon, and Bickel-Green, this is still invariant, but are there relations between these two? Okay, my conjecture is that yes, they are, but exactly what are they? That is a work in progress. And general correspondence theorem will be okay to actually put all of these relations together, or see if by use the tropical geometry we can actually have an explicit correspondence. I have to say, for degree 2 extension, this is actually a preprint that we have with Sabrina, Hannah, and Felix. So the co-author for this Caparrós-Harris formula that we will put on the archive very soon, but we have already proved it. There is a correspondence theorem for degree 2. Now the problem is, for general case, then well, with that we still don't know. Like we know the correspondence theory will work if we fix the degree, but of course, if we want arbitrary degree extension, then we need to have other kind of tools. But yeah, that was what I wanted to talk about. So thank you for your attention.